So, okay, so welcome back. So I'll continue with the third part of this tutorial, and I'm gonna go again at a very high level, give you some of the ideas for maybe a bit more advanced data linkage techniques, including different blocking or indexing techniques, and some different types of classification techniques which have been developed in the last few years. And in the fourth part, then I talk about privacy issues before we wrap up. So one technique which is quite successful, implemented in several very large-scale data linkage applications, is called the sorted neighborhood approach. The idea is basically that instead of building blocks, something happening with the light here, instead of using blocks, we sort the database according to a sorting key, and then we have a sliding window which goes over the database. And depending on how we sort the database, hopefully similar records are being put into the same window, right? So an example given here is that we have first and last names that concatenated into a string. So Abby Bond, Paul Smith, Pedro Smith. The whole database is sorted. So don't worry about these are just record identifiers. And then we have that sliding window going over the database. The nice thing with this is that depending on the window size, we have a linear complexity. So the database times the window size gives us a number of potential comparisons. The original approach was using a fixed window size. But as you can see here, I highlighted this with the thick bars here. We can also do this in an adaptive way, that we're basically looking at these sorting keys. And if the sorting keys are completely different from one record to the next, like from Peter Smith to Robin Stevens, then we can actually adaptively set the size of that window, and that further improves or further reduces the number of comparisons we have to do. Right? So there's a few papers on this. It's been used, as far as I know, in Germany in an application which does matching of credit data in a big company. So a highly successful technique. I'll talk a bit more about this. So this is based for static databases and batch matching of one or two databases. Forgot to mention, if you have several databases, you put them into one long list and you kind of merge them together. But we developed a dynamic approach which basically allows us to do this for real-time matching of dynamic databases. I'll talk more about this tomorrow. Canopy clustering is another idea which has been developed. So that's an overlapping clustering technique where we try to have a very simple, very fast similarity measure. And that's, again, what's often being used is Jacka similarity based on Q-grams, like what I explained before with Q-gram-based approximate string comparison. We basically do a clustering in a way that we randomly select a record, so like a centroid. We said that's a centroid. We then add all the records in a database which have a high similarity with a certain threshold, a loose similarity into that cluster. So these would be the large clusters here. So this will be cluster 1, this will be cluster 2. So we add all the records with a certain similarity into that cluster. Then we remove from the data set all the records which have a similarity, which the tight similarity. So for cluster 1 over here, all the records in this area are included in the cluster. All the records in the smaller radius are removed from the data set, and we repeat the process until every record is in a cluster. And then each of the clusters becomes a block. And depending how we set these thresholds, especially how we set the tight threshold, we get more or less overlap between the clusters. So a record can be inserted into more than one block, unless I set the tight similarity the same as the loose similarity, in which case there won't be any overlap anymore. And again, this has been shown to be fairly successful. It's often used in computer science research, also due to the availability of an open source package which has implemented this. Another technique which we did a bit of work on earlier is, again, using Q-grams. So for certain data sets where the values are very messy, so where we don't really have a clear high-quality blocking key, we came up with the idea of using Q-grams again. So we generate Q-grams from our records or from our values. We then generate subsets of these Q-grams, and if certain subsets are the same, then we insert records into the same block. So for example, for Peter, we generate, that's the list of all Q-grams, we generate all possible subsets with one Q-gram removed. And if we do the same for Pete, then we end up Peter and Pete having the same list of Q-grams, so we insert them into the same block. So this works quite nicely if we have really messy data sets, but because we generate these sublists, computationally it's very expensive and it doesn't really scale up very well. Another approach we just mentioned briefly is the idea of mapping strings into a multidimensional space. So we're building a multidimensional space where certain strings are pivots, and then we convert basically the string similarities into distances into multidimensional space. So every record becomes a point in that space, and we compare records if they have a certain minimum distance between each other in that multidimensional space. Okay, that's been used, has been proposed about 10 years ago. The problem is it's highly sensitive with regard to the dimensionality of that space, and then also we require multidimensional spatial indexing techniques to actually scale, to make sure the whole thing is scalable. One thing I'm going to talk a bit more about tomorrow is controlling block sizes. So most techniques, standard blocking, canopy clustering, they generate blocks of different sizes. Sorted neighborhood is one technique which gives us the same block size depending on if the window size is fixed. But in certain applications, we need to be able to control the size of blocks. So for example, there's real-time matching, where we can, let's say we have a query record which we want to match with a database. We can only do a certain number of record comparisons because we have a time limit before we have to return a match. So like in a credit, so application of credits, for example, where a customer goes to a bank, provides their identifying information, the bank does the credit check with the credit bureau, they have to return a match or non-match within a very small period of time. So the large, if you cannot control the block size, then for a certain record you might have to compare that query record with lots of database records. On the other hand, with privacy preserving record linkage, I'll come back a bit later on, we want to have a minimum block size to kind of make sure that small block sizes would reveal some private information. Certain machine learning techniques have quadratic or even higher complexity in the number of records in a block. So again, we want to limit the maximum block size. So the idea which we've developed, and I'll talk more about how it actually works, is we do an iterative splitting and merging of blocks with regard to different blocking keys, right? So if you have a database, we do a first blocking, we then merge small blocks, we calculate similarities, blocks which are too big, we split, we merge, we split, we merge, and different clustering techniques, we end up with blocks within that blocking range. It gives us very nice results. Okay, so a bit more about advanced classification techniques. As we saw before, the Felici and Santo, the basic approach, first of all, we compare every record pair individually. We end up with matching weights, which are then summed into a single number. Instead, we could basically use all the similarities which we calculate for the individual attributes for binary classifier. And this binary, I mean, we don't want to have potential matches, we just want to have matches and no matches. So we don't have to do manual clerical review. Or maybe there's an application where we don't have the capacity to do manual assessment of possible matches. Okay, many machine learning techniques have been used. If you have supervised, if you have training data, then we can use support vector machines, decision trees, neural networks, etc. I mentioned the learnable string comparison, so we can learn the edit costs, which can improve our linkage and basically modify our similarity calculations. If we don't have training data, we can use active learning. So basically, we'll give difficult to classify record pairs to a domain expert. The domain expert does a manual classification, like in the clerical review, but that information flows back to build the classifier, and we do this several times. So again, I'll talk more about this in my talk tomorrow on some techniques which we've developed. Unsupervised, we can do clustering. So basically we cluster all the records which we believe are about the same entity into one cluster. So the challenges we have to deal with in general is that in most applications we don't really have training data. Again, potentially we might have some data from an earlier matching process, so if we do data linkage on a regular basis, or we have data from a clerical review process. Again, the challenge with that is that it's very easy to classify the high quality matches as being matches and the records which are completely different as non-matches. The ones in the middle, the really difficult cases which are given to clerical review, these are very difficult to classify record pairs. So the question is, how confident can we be that that clerical review process is highly accurate? So what sometimes is being done is that instead of only a single person looking at a difficult to classify record pair, it's given to several people and the majority vote is being made or reassessed by several people. So if two people say this is a match and the third person says it's a non-match, then the decision might be that becomes a match. We don't have gold standard data available, so we don't know the true match status in many cases, and again it's very difficult in certain applications to actually get the truth, especially I guess if it's historical data. The people in these data sets have died, right? So we can't really be 100% sure if two records in two censuses across 10 years period are actually the same person. We also don't really have large test data collections available. In computer science and information retrieval, there are large test data collection, track collection. In machine learning, we have the UCI machine learning repository, which contains hundreds of different data sets. But in data linkage, we don't really have that. We don't have a collection of data sets which allows us researchers to work with and play around with and compare algorithms. And again, it's mostly because of privacy and confidentiality, because we need names and addresses to work with. We cannot use anonymized data or encoded data, because then we lose the whole issue of typographical errors and variations and things like that. That's why a lot of research in computer science has basically used bibliographic data. Which is publications where we have authors, where we have titles of papers, venues, and we have the same issue of typographical errors, abbreviations of conference names and things like that, which makes it a very challenging problem. But that also means that many of the algorithms developed for bibliographic data, you can't simply take them and now apply them on personal data because the characteristics are quite different. Right, so just very briefly, so active learning. So this is a semi-supervised approach or semi-supervised technique. So we're basically, we have an interaction between a learning algorithm and often a domain expert, or alternatively, in the last few years there has been work on using crowdsourcing. So basically, Amazon Mechanical Turk, that data is being given to people on the web, and they do, for a certain amount of money, they manually assess individual pairs of records. Again, that's possible with bibliographic data. I guess that's possible with consumer products and things like that. But you wouldn't want to have your medical database given away for crowd-based assessment, right? So that's, again, an issue where supervised active learning in a closed environment is important. So the idea is basically that we select a sample of record pairs which are difficult to classify and give them to domain experts. Often there is a budget constraint, so we can only classify a maximum number of record pairs manually, time-wise or money-wise. So the question is, which are the best record pairs to give to for manual classification, which helps the classifier most. So we don't want to give a classifier randomly selected record pairs. As we discussed before, most of them are going to be non-matches. We don't want to give record pairs which are highly similar to the manual classification. We want to select pairs which are highly difficult, so the ones which are close to a decision boundary. And we do this in an iterative way. So after each, after a set of manual classifications, we retrain a classifier and then select another set of examples to manually classify. So talk more about this in my presentation tomorrow as well. Another avenue of work has been group linkage. So again, this is in applications where we have not just records about entities, but also groups of entities which somehow have to be linked together. So this is, for example, done on bibliographic data where you have publications written by the same author in different databases, which helps us to decide if two authors are the same, or in historical or in census data where we have a census certificate or a household or family where we can basically use the similarities between individual people across two censuses. We know that they're in the same family, so we can use the information. And it's a combination of using individual attribute similarities, then calculate the group similarity. Again, it's been a bit of work on combining this with supervised learning as well. So here's an example of some of the work we've been doing. The idea is, so this is a graph-based linkage. So each of these graphs here illustrates a household in a census database where each node is an individual. The dashed lines are the attribute similarities which we calculate, so based on names and addresses. And then the graph is now, again, that's just an example, the information which doesn't change, right? So for example, the left graph is from 1861 and the right graph is from 1871. Information which shouldn't change between the people is their age difference, right? So husband and wife, which are 2 years apart, should still be 2 years apart in 10 years' time, right? As I mentioned before, because of the other quality issue, we observed age difference changes up to 5 years, right? So the husband, because the people didn't know how old they were, it's quite interesting how they grow older over time. Of course, then the differences are changed as well. So the example here with husband-wife is a 2-year age difference, over here is a 4 age difference. But the overall structure between these two households, you can see there's 2 parents, there's 2 children, so these are the age differences between this parent and this child. Overall, they should stay similar, even though they might change a little bit. But these structures are going to give us more information if you want to link households together over time. So we're going to basically generate these graphs for each household, and then we do a graph matching for all the households which have maybe even at least one single record has a high attribute similarity. The challenge, and that's what we're working on at the moment with colleagues in Germany, is of course households don't stay stable. A 10-year period of time, children move out, babies are born, grandmother dies, and things like that. So we actually have to also look at an evolution. So we might have 4 people in a certain census, which end up in a household of 5 people 10 years later on, or the daughter marries and goes into another household, or they start a new household, and so on. But the basic idea is for these techniques is to use the structure of the relations between people and things which don't change over time to improve the matching of groups. Okay, another quite large area of research has been in the last few years what's called collective entity resolution. And I'm going to give you just a basic idea. There's several different techniques. So instead of just looking at the attribute similarities between pairs of records and calculate and deciding if a pair is a match or not individually, collective techniques look at the whole database or build a graph of the whole database and look at the relationships between entities. And again, most of this work has been done on bibliographic data, where we have, as the example here shows, we have papers, we have authors, we have venues, and even affiliations where people work. That allows us to build a very complex graph and connect different entities or entities of different types together. Then we can use these relationships to decide if certain ambiguous links are actually true links or not. So in the example here, which is from Kalashnikov and Marotha, from a database journal in 2006. So we have a database of authors. We have a Dave White, a Don White, Susan, etc. We don't know where these 2 authors are. And we have a table of papers. And in here we have 2 divides. And the question is, are these two divides Don or are they Dave? And we can build a graph such as that, so where basically these are the links which we get from our tables, and these are the links where we don't know what the weight is. So we have to basically say if a weight, set a weight to 1, which means we link them together. If a weight is 0, we don't link them. And the question is D White in paper 2, is it Dave or is it Don? And in paper 6, is this Dave or is this Don? And in this specific approach, we basically use a random walk approach. So we're basically looking at, well, if this would be Dave, so if this would be Don, then how many links do we have to go to complete that cycle here? If it's Dave, how many links will we have to do to get back to Dave, right? So this again is just one example. Other approaches I've looked at relational clustering, where we calculate similarities between nodes depending on how many neighbors they have. So if I'm linked, if I have a high similarity with another person, and that, let's say another author, and that author only has no other co-author, then it's more likely that they should be linked compared to if that other person has 100 different co-authors. So we're looking at these relationships and ambiguities to do our collective linkage. Okay. Transitive closure is a thing we have to consider as well, and with some algorithms it's done as a post-processing step. In other algorithms it's done as part of the classification. So the transitive closure is basically if you have a chain of records which we link together, then all pairwise links, all pairs of records have to be matching as well. So if, for example, we say that A1 is the same person as A2, who is the same person as A3, then of course A1 and A3 also have to be the same person. And the problem sometimes is that we get these chains of links. So we might have a certain name, a certain address, then the address changes but the name is high, and at some stage the similarity between A1 and A4 might be very low. But because pairwise they're linked, we then have to decide where do we split these chains, right? And certain clustering techniques, they, for example, limit the length of these chains. If you know from domain knowledge, we can only have 3 people matching or something like that, 3 entities matching, sorry, 3 records matching. And in others, we just basically built the transitive closure and said all the records which have at least one high similarity into the same group. Oops. Okay, now another aspect is synthetic data, and we call it generating synthetic data. I talked to somebody and said it's more simulation. Just to clarify, I think the statistical community means something different with synthetic data to what I'm talking about here. So the idea of generating synthetic data is really because it's very difficult to get access to real data. And the main purpose of us generating synthetic data or simulating data is so we can test our algorithms with regard to, let's say, scalability. So we might have a small real data set, but how does a blocking technique or an indexing technique work with if the data gets larger and larger? If we do generate or simulate synthetic data, then we can control all kind of parameters. So we can generate how many records we want to control, how many records we want to generate. We can control what kind of errors to introduce. So we can, for example, introduce typographical errors. We can introduce phonetic errors, and I'll show an example on the next few slides. We can control how many duplicates to generate and things like that. Another advantage is that because we've generated the data, we know which records should be duplicates of this, are duplicates of the same person. And of course, we can also publish the data, and we can publish the data generation program as well. So here's an illustration. I'm not sure if you can read this one with very small font. So basically, we were looking at what are the different ways of how errors can be introduced when data is being generated. This work done by a student about 5 years back. So we looked at, we can have printed documents, we can have handwritten documents, or we can have our memory. Somebody can read, dictate the printed or the handwritten documents. Somebody can talk about what's in their mind. We can type things in. We can read and type these documents. We can character recognize print and handwritten documents. So far we can't scan our minds, right? So there might be a new error coming in a few years' time. OCR introduces errors. Dictating, speech recognition introduces errors. Typing introduces errors. So what all these errors mean, basically, what are the different types of errors which are likely going to be introduced as information is converted from paper-based or from your mind into a document. And it's either changes at the character level, it's phonetic changes, and it's optical character recognition mistakes. So based on these characteristics, we then developed a synthetic data generator, which is really about introducing the errors which we would expect in certain situations, right? So here's an example of what we generated. We give each record an ID. So org means these are original records which we generate maybe from a telephone book, so based on frequency tables of first names, addresses, last names, etc. And then we start to generate duplicates of these records. So the first ones up here are typing errors, for example, or abbreviations based on lookup tables. So instead of having a circuit, we have circuit. These are abbreviations which are valid. Or we have typing errors here. The second record is now based on phonetic variations. So this is actually where we re-engineered phonetic encodings like soundex and double metaphors. Instead of having a string and converting it into a code, we look at all the rules, the phonetic encoding rules, and we use them to modify strings with regard to phonetic variations. So you can see again, Contreras, Contreras, Desiree, Desiree, Barawang, Barawang. So this allows us to simulate data which contains errors. And then we can use that. We can validate, or we can vary the rate of errors and what type of errors, and that allows us to generate data which we can use to try to relink things back together. Okay, that was very brief, actually. Are there any questions on this? I really want to give you a very high-level overview of some of the ideas. Okay, so let's move on to the privacy aspects, which again link together with maybe better with the program here. So coming back to the question from you before, what's the objective, right? So here we assume we have data in different organizations, and maybe the law in a country or regulations prevent that the data can be given to another organization. So what we want to achieve here is that we want to be able to link records together without any identifying information having to be given away. So can we encrypt and code the data locally, use these codes to identify similarities between records. So we still need to be able to allow approximate linkage. We have to be able to assess linkage quality and completeness. We have to be able to techniques which are not vulnerable to any kind of attack, and the techniques should be scalable to link large databases and also across multiple databases as well, right? So the thing is that at the end of such a privacy-preserving linkage, I'll give you an example in the next few slides, the database owners might still be interested or will be willing to reveal some information of their linked entities to an external party. So I hope it becomes very clear after some of the example here. So let's say we have a demographer at the university. She wants to investigate how mortgage stress is affecting people with regard to their mental health and their physical health as well. Right? So people who have bought a house, got a large mortgage, interest rates go up, they're really struggling to repay their mortgage, how is this affecting their life? So to do such an analysis, this demographer would need data from financial institutions, so from banks, from government agencies, with Social Security, from health, from mental health institutes, for example, maybe from education. Maybe there's a correlation between the education, the level of education of people. There could be all kind of other databases which might be useful for such an analysis. Actually, also need, so that's kind of from government institutions, but also from maybe private health insurances and so on. It's very unlikely that this researcher can just go to all these organizations and ask for these databases. To do the linkage, again, she would need to have access to names and addresses from all these databases to identify people with certain characteristics, which she wants to basically build. What's people's education? Where do they live? What's their family situation, etc. She's not interested in the actual people. She's not interested if that's John Smith or Lucy Miller, but she needs to know their age, their gender, their postcode they live in, their income, their employment status, etc. Right? So getting access to all these databases is pretty much impossible. So how can we do such a linkage? That's the big question. So current best practice approach would be that there's something which is being used, I think, worldwide now. It's originally developed, I think, in Australia in the health domain, that we basically separate the identifying information, so names and addresses, etc., which we need for the linkage, from the payload data, which is what the researcher needs later on. So we give the identifying data to a trusted linkage unit together with an encrypted identifier. So the linkage unit doesn't get any data about the education status of the person, the employment status, etc., etc. She only gets names and addresses and maybe dates of birth. Based on that, the linkage unit can do the linkage, assign it again an encrypted identifier, and send that back to the data sources, which can link that together with the payload data and then send that to the researcher. I think there's an example on the next slide here. Again, back to the example from before. So we have names and addresses, financial details, names and addresses, dates of birth, health details, names and addresses, and education details. All the names and addresses, the identifying data is being sent to the linkage unit to do the linkage. The linkage unit doesn't learn anything about that payload data. The identifiers of the linked records are then sent back to the database owners, and the database owners now attach the payload data and send that to the researcher, and the researcher can now basically do a linkage based on these encrypted identifiers. So the researcher, she never learns anything about the people. She gets all the information of the linked people, and again, there's of course the potentially she could re-identify people with certain characteristics. That's still an issue you have to deal here. I think I've talked about, yeah.
What's the sense in which you mean that previous slide to be best practice?
That's what the paper was called. So that was from 2002. Best practice. No, so that was kind of, okay, that was developed by health researchers, and that's being used, as far as I know. Christine, you might correct me, you're better connected to these people. It's still being used in several health data linkage units, at least across Australia, but I think in other countries as well, right?
Yeah.
Yeah, so they're basically the separation of the identifying information from the payload. There's different variations of, but it's still being seen as a best practice approach, right?
So the definition of best practice here is trusted third party does the linkage.
Yes.
Delivers to researchers just enough information to do the analysis that presumes the linkage is correct.
Yes, that's correct. Yeah.
We
And
might
again,
be guilty of that too.
sorry?
We might be guilty of that too.
Yeah, and I guess that's the last slide nowadays. So the promise is that the linkage unit still gets all the identifying information. So even though they don't get the payload data, even knowing where the data is coming from reveals some information. Right? If a table is from a mental health database, then everybody in that database is somehow connected to mental health issues. Right? So There's still the problem of collusion between parties. Maybe that doesn't really happen in a health domain, that hospitals are probably not going to work together to try to identify by others' patients. But there's still the potential of internal attacks, of internal and external attacks. So the data is still vulnerable. It's sitting in that trusted health linkage, the trusted linkage unit. It still names and addresses and things like that. So what we're trying to do is what we call privacy-preserving record linkage, to basically make that process much more secure, that the linkage unit never sees any unencoded information. So we still do that separation, I guess, between the linkage here and then the linkage unit gets the identifying information. But instead of having to send the unencoded data to the linkage unit, we want to make sure that the linkage unit never gets any sensitive information.
Can I make a comment?
Yeah, sure, of course.
Just, it isn't sort of done one-off either. These are population-level data linkage initiatives, and so they link administrative health data ongoingly over years, decades. Okay, so they're actually creating de facto population registers, and that's one of the concerns, I think, that is another concern that's perhaps not there.
Okay.
That a data linkage unit, by creating this de facto population register, it actually increases the accuracy of all the linkage ongoingly. So it's a way of having extremely high quality linkage, but at the price of, having all of that sensitive information available at the linkage unit and creating this sort of de facto register.
Yeah.
So actually kind of my question, so I'll frame the question as well then. Does privacy preserving record linkage also operate entirely one-off, or does it have that kind of ongoing population register aspect as well?
Good question, yes. I think at the moment we're at the stage of where we're still looking at the actual techniques of how it would be best linking the privacy preserving. Again, Rainer maybe be able to comment on this as well. He's been working in the area. I think at the moment I'm not aware of a linkage unit which only uses privacy preserving techniques. At the moment we're running some experiments in Australia looking at our techniques and do we get comparable accuracy. But I think the end aim would be to use privacy preserving record linkage to build up. So basically, as you say here, so at the moment we're basically building up chains of, or kind of a linkage spine, or whatever we call it, basically a chain for every person and how they're linked to different databases. And then from that we can extract subsets of linked records with people with a certain characteristic. Yeah.
The Administrative Data Research Network in the UK uses this sort of trusted third party thing. In your next slide, I didn't understand the next slide. You said that the linking information is encoded.
Yes.
How does that work? Surely the actual information which is used for the linkage has to remain as it was, so that the linkage can be carried out.
No, I come back to this in the next few slides. So that's the techniques where we use Bloom folders and all kind of hash encoding. Right? So again, the challenge really is to overcome the issue of typographical errors, and because you can't do you can't simply hash encode things and then look at the encoded hashes, right? So I'll try to explain this on the next few slides. Right? Yeah.
I guess two questions that are quite different. So one, if you go back to the slide with the picture, with the red, so how do people sort of think about the issue that just the red stuff linked together, even though it doesn't contain kind of names or addresses, could easily contain enough information to identify people?
Yeah.
So that's my first question. Just like I guess it's a statement and a question.
Yes.
So the statement is it could easily contain enough information to identify people. The question is how do people in the community that's looking at record linkage think about this?
Yeah. So I guess it's a separate, in a way, what we want to do here, we want to make sure that the linkage unit doesn't see doesn't have to get access to a sensitive information, right? So we can link, we make the step, the linkage step here.
Yeah, I'm not talking about what the linkage is.
No, but so I mean, okay, so in a way, I know the communities are fairly totally separated in a way, right? So, and I guess that's the great thing being here, that we kind of think about how can these two communities maybe come up with better ways to do things together, right? Because I guess the re-identification problem is still there after we've done the linkage. Completely agree with that. And I get these questions almost every time I talk about this, right? So, but that's another thing that you guys are here, right? That you can really think about, is there any way we can, come up with something combined, right? Yeah.
The Administrative Data Research Network, once you've got to the researcher, you've linked the data, so that this is relating to your question. Any analysis on that is done by approved researchers, by accredited researchers on approved projects in secure environments. And the only thing which comes out of that is the statistical summaries, the aggregates and so on, the papers, if you like. So it's, from researchers, there's another ring of security around that.
He has the same question about the papers, but we'll delay that for later.
Yeah, I think the same in Australia as well, right? That there's all ethics approval. I'm not sure about the secure, if it's done on a secure server. I don't know. Actually, James Boyd, who is the director of the Western Australian Data Linkage Unit, he's going to be here in September, and I think he's going to hopefully talk about this, how they actually do this, right? So, yeah.
When you release information about linked units, do you also provide the probability of linkage?
Very good question, right? So again, I'm not sure how it's done in practice. My understanding it's not really. So you just basically say these two individuals or this information is about the same individual. That's a big loss of course of information, right? So
also, since you don't give to the linkage unit the red part, I think this red information, the sensitive information, could be also used to improve the linkage quality.
yes, I agree as well. Yeah.
So,
Yeah, and again, I mean, this is just a very simple example. Of course, you can potentially, again, date of birth, you might release age of people, right? So the researcher here might get the age of people, right, but not their date of birth, if that's important for a certain analysis, right? Potentially, again, there might be something like, is there anything in common between financial education, which might be useful for the linkage, right? So there could be different situations where the payload data, it's not just identifying information, it could be something which is useful for the linkage as well, yeah.
Just to address maybe I think Adam's comment / question is, I think you have to be really careful with the red areas, because there's a large number of data sets that are publicly available online where you can merge the 3 of the red data sets per se, and you can identify using linkage techniques about 80% of the individuals uniquely,
Yes,
which is a major problem for privacy.
that's right, yeah.
So given that, why bother? I mean, if you're trusting the researcher is not, if the information that's being handed to the researcher at the end of this pipeline is easy to re-identify, and you're relying on the researcher's sense of ethics, why not just rely on that? Like that, basically,
Yeah.
the system
Yeah.
is sort of no stronger than the weakest
Yes,
part of
that's,
it, right?
yeah. But there's also rules and regulations in countries. So one example I know about is in Switzerland. I can remind you must probably know more about this. So they have a cancer registration for children, and a cancer registry for adults. And apparently by law, they're not allowed to link them together. So exchange data between the two registries, right? So the only way they can do this is by doing a privacy-preserving linkage, so that only hash codes and whatever is being exchanged. So for children who survive into adulthood, you couldn't actually use that approach because the law doesn't allow data to be given to original unencrypted data being given to a linkage unit. Okay, Ryan, you might know more about this project, I think.
We have to operate in legal environments, and therefore we have to operate in legal environments. And for example, to get the legal permission to use a database usually takes 2 years. And we can do all kinds of dirty tricks, but we are not allowed to do so. And if you have to rely only on the databases you are allowed to access, you need 2 years to get one. And so everything is quite difficult if you want to stay legal, and as an official organization, you have to stay legal. So it's quite complicated process in practice.
Can I make another comment as well, perhaps? I mean, when I first started reading in the privacy-preserving record linkage literature, I thought privacy meant privacy for individuals. And it actually doesn't so much. I mean, that's a bit of a nice byproduct that it helps a bit. But what it really does, it's more like distributed linkage or something. It allows linkage of distributed data sets without having to either give your data to each other or to a trusted third party. So while that has some nice byproduct of helping with protecting privacy, it's not actually the main game. And the main game, as everyone's been saying, is actually to get around laws against sending personal information outside the custodian's system.
It's more anonymisation
does that help?
than private, making it private, isn't it?
It's not actually about individual privacy. It's actually about something else.
Okay, thanks. Okay.
It took me a while to figure that out. So when someone says privacy, you have to ask them what they mean.
Yeah. Okay. So right. So discussion. So where were we? We were somewhere here, right? So so the basic idea, coming back to the data linkage process, is really to have most of the steps in a way where it works only on encoded or encrypted data. So everything in the yellow box here would not be on actual names and addresses and dates of birth, but some form of encoding, right? So that the data pre-processing can still be done locally, but then it's being done again at the linkage unit or encoded between the parties as well, right? So the clerical, again, at the end of the process, we're only going to reveal some information about the matches, as you saw in the previous example, right? For the clerical review, that's an open question. Can we do this in a privacy-preserving way? Not really, right? It's difficult to do clerical review on encoded values. So, but can we somehow reveal some information which helps clerical review? So the two basic types of protocols, we can either do it just between two database owners, or we can use a linkage unit, trusted, semi-trusted. The main steps, again, I explained at a very, very high level. It's usually that in the first step, there's an exchange of keys, of parameters, of which techniques to use, how is data pre-processed. In the second step, then Alice and Bob, the two organizations, do that pre-processing and encoding. Then they exchange their encoded records, or in certain ways, and that often that's being done in several steps. And then at the end, in step 3, we kind of exchange the linked records or some information about the linked records. If we have a third party, we can, again, Alice and Bob would set up the linkage parameters and secret keys, etc. Send the encoded encrypted data to Carol, which does the linkage, and then sends the results back of the linked records, right? So basically the identifiers of records which have a high similarity. We can extend this into multiple parties, so more than 2, which makes things more challenging. Again, with or without a linkage unit. So what are some of the characteristics? We have to look at what's the adversary model. We can either assume that the parties are honest but curious. So basically assume that the parties follow a protocol, but they try to learn as much as they can from all the information they receive from any other parties. And most existing privacy-preserving record linkage techniques assume that model. The second model would be the malicious model, where we assume parties do not follow a protocol, which makes things much more difficult and often result in more conceptual algorithms or techniques which have a much higher computational complexity. There's a few more recent techniques, accountable computing and covert model. They haven't really been used in privacy-preserving record linkage. That's something I like to do with my research group in the next few years to somewhere in between the malicious and the covert model. what kind of attacks do we have to protect or consider? The first one is a dictionary attack. So we encoded that. I'll give an example of how the encoding works in the next few slides. So where we assume that an adversary has, let's say, a telephone book which contains all the names and addresses of people in a country, and they can basically try to identify the encoding technique. And once they have a match with of a code, then they would reveal the source or the original value of that record. We can do a frequency attack. So we're basically looking at the distribution of hash codes or encodings, and if you find there's a close match between a frequency distribution of an unencoded attribute and an encoded attribute, then that reveals some information. There's an illustration here. So let's assume we have sorted surname frequencies, sorted postcode frequencies, and hashing codes. I'll talk more about hash encoding in the next few slides. So maybe this is taken from a telephone book. So if you look at this, you can see that that's the surname distribution. So this is likely going to be the Miller and Smith. And over here we have all the much rarer surnames. And if you can see that hash codes follow a similar frequency distribution, then we can infer that these hash codes are about surnames. That gives an initial starting point to them. Maybe well, we can basically say the top frequent hash codes, they must be the top frequent surnames, which is initial starting point to do further analysis and attacks. There's also something called a cryptanalysis attack, which kind of is a special category of frequency attack, which is specifically to Bloom filters. I'll talk more about Bloom filters in the next few slides, which is one of the most recently common used techniques in privacy preserving record linkage. So here we look at the frequency of individual bits in a Bloom filter and how often they occur, and based on that we can then basically identify bits and pieces of values. So if SM is a common Q-gram because it comes from Smith, once we know the encoding of that SM Q-gram, that gives us again a starting point. We also have to think about collusion. So what happens if two or three parties work together with the aim to identify sensitive data from a third party? That in certain protocols this is a problem as well. Okay, so what are some of the techniques? So initially, privacy preserving record linkage, the first techniques were developed in the mid-90s by French health researchers who, again, they wanted to link data across, I think, different cancer registries, and they basically use simple one-way hash encoding. And I'll talk more about this on the next few slides. Simple hash encoding doesn't really allow you to do approximate matching, so you find all the exact matches, but if you have Peter and Pete, it doesn't work, right? So the second generation in the early 2000s was basically developing secure approximate string comparisons. So for example, there is a privacy preserving version of edit distance where two parties have two strings or sequences, and at the end of that protocol they only learn the edit distance between the two strings, but nothing else. But of course that, again, going back to the that of course reveals some information as well. But if I have Peter and I learn the edit distance to the other string is 1, then I can kind of think what are other possible values which are names. Could be Pete, could be something else, but the amount of, it still reveals some information, there's some linkage, some information leakage. There's also other techniques. In the mid-2000s, researchers had to look at the scalability issue, so basically looked at blocking techniques. How can we do blocking in a privacy-preserving way? And again, there's different ways of using hash encoding. And there's been there's 30-odd techniques which use all kind of techniques, combination of existing privacy techniques. One of the ones that's been very successful is Bloom filters, which Rainer proposed several years back. And I'm going to talk more about those a bit later on. Right? So at the moment, I wouldn't say there's a single clear winner. I think Bloom filters is very successful, but there's still other techniques which are being worked on as well. So I mentioned hash encoding several times, so that's one basic building block. So you might be familiar with one-way hashing. So it's a Q-hash algorithm. It's one which is used in internet commerce and e-banking and things like that. So it's a function where in goes a string, out comes a hash code, a bit pattern. If you only have the bit pattern, it's almost impossible to get the string right. So, yeah.
Sort of a broader question, maybe before you dive into
Okay.
the details. What sort of the list of things you had on the previous slide? They all kind of do very different. Like they achieve very different things.
Agree,
in
yes.
terms of
Yeah.
what security guarantee they provide. So can you say more about what the goal is in terms of the security you're trying to provide?
Okay. Well, again, I guess it's with regard to the different attack methods and what models there are, right? So, if that,
So even for each of these three models, this is sort of the class of adversaries you're willing to
yeah,
want to tolerate. I guess my question was more,
What is the goal of the adversary?
what is the goal?
What is the win for the adversary?
the win for the adversary would be to basically learn the unencoded values, the John Smith and his address and things like that. For the majority of the database, ideally for the whole database. Right. So basically identify, the adversary learns the identities of the people in the database we try to link.
Are you assuming anything about like how the data, where the data, how the data is generated? Do you have any sort of are you making
Not
a model and
really,
assumption
no.
about the data?
No, because again, we want to
Or about what the adversary knows about the data? Right.
Auxiliary
Is
information?
there an assumption about?
in certain.
I guess.
Okay. Yeah. I know.
yeah.
Okay. Yeah. I know what you mean. So.
I come from I come from a crypto background.
Yes.
That's kind of where I grew up, so to speak.
Yeah.
And so the kind of at the beginning of this section of the talk is where I sort of I'm looking for like just a clear problem statement
Right.
that is self-contained and independent of the technique you want to use to achieve it.
Yeah. And again, I think different techniques have slightly different problem statements as well. That's kind of, it's still an evolving research area, I would say. And again, it's worked on in many different areas, like Rainer is a sociologist. It's done in computer science, it's to some degree done in the health area as well, right? So it is a bit of a mess, I would say, right? There is no clear definition, I would say, in many cases, right? So, so one thing we've been looking at is we assume that an attacker has access to a global database, which could be a telephone book, and try to identify how many people in an encoded, how many records in an encoded database match to one or more records in a global database. So we came with a disclosure risk measure, which actually not going to talk about today. So we're looking at how many people could we do a one-to-one identification or one-to-many identification. But again, in certain papers, in certain techniques, they don't even consider this, right? So it's not a clear, defined problem statement, attack statement. It's again something which we should work on the next few months, right? So, and again, that's where your community has a much better, it's at a much better state than I guess the privacy-preserving record linkage community maybe. I hope that answers your question.
Yeah, no, it did. Yeah.
Where were we? Okay, so we were here, right? So this is basically a building block. Again, that's how the first privacy-preserving record linkage techniques work, right? So we hash encode, like the example here, we use a hash function. If two codes are the same, then we know we have an exact match. If they're different, we don't have a match, and of course that doesn't really work in practice. That work I mentioned by the French health researchers in the mid-90s, they also did phonetic encoding, so we can of course convert picture into soundex codes and then do hash encoding on the soundex code. That gives us a bit better matching quality, but it doesn't really work in messy data. Then this is, sorry, yeah.
I have a question on the previous slide. I don't quite understand why only exact matching is possible for the hashing.
So if you do a simple so basically if you take a value, a string, a name, and we hash it, then we get a bit pattern.
Right, but you could do more than exact matching. You could do something like min-wise hashing.
Yeah, okay, so that's a very simple, I'm assuming here we use a one-way hash function. You can do all kind of more sophisticated hashing, where you basically generate more than one hash code. So you can use LSH and min hash and things like that, and then look at how many of these hash codes. This is just a basic, simple one-way hashing, right, of a string into a hash code. The hash codes are the same, it's a match. If not, then they're not a match, right? Then yes, so this is a technique which Rainer proposed in 2009 in a biomedical journal, which I think I found interesting, again showing the multidisciplinarity of this area. So Bloomfield is a bit array, where we basically map elements of a set into the bit array, and we set the elements to 1. So then we can basically calculate the similarity between these bit arrays, and that has shown to be fairly successful. So I'll give you an example here. So again, we have Peter and Pete. We convert them into Q-grams, we hash map them, and then we again calculate the dice coefficient, so how many bits are set to 1 between two Bloom filters. So the example here is we have Peter gives us 7 bits, Peter gives us 5 bits, 1, 2, 3, 4, 5 are in common, and therefore we have a similarity based on that of 0.83. And of course, this issue of this collusion, which gives us some false positives, so increases the similarity. Going back here, again, it depends on how long you set your Bloom filters. There's different variations of this idea of we can either have one Bloom filter per attribute, or we map whole records into a Bloom filter. We can give different number of hash functions for different attributes. So for example, we know that gender contains less information, I guess, to distinguish people than first name. So we give more hash functions to first name compared to gender, and so on. There's been a whole bunch of papers looking at this. We can also do blocking based on these Bloom filters. So we can do, again, min hashing on these, or Hamming-based hashing based on these Bloom filters. So there's a lot of work happening in that area. And again, I'm sure Rainer will talk about this in September, more about the most recent work on this. Okay, so just again, don't look at this if you're coming from cryptography. They're just trying to give you some of the ideas behind multi-party computations. They're very, very simple for people who have never heard of this. So the idea is that you want to compute a function across different parties such that at the end, everybody learns the output of the function, but nobody learns the input. And this is a very, very basic example of a secure summation. So let's assume we have 3 hospitals. Each hospital has a sensitive number of patients with a certain disease or so. We want to find out what's the total number of patients across these 3 hospitals. The idea here is, so we basically want to calculate the summation here. The idea is that the first party selects a random number, which is kept to itself, a secret number. It adds its own number to this, sends the sum, in our case, 1054 to party 2. Party 2, because it doesn't know the random number, doesn't really learn anything about the first sensitive number. It adds its own number to it, which gives us 1127, sends that to party 3. Again, party 3 doesn't know anything about the initial random number. It adds its own number to it, sends the sum back to party 1, which can then subtract the random number and gets the sum of the final summation. So this is probably the most simple building block for secure multi-party computation, and based on those we can do more complex operations. Okay, so I think that's the end of my really very brief general overview of some of the ideas with regard to privacy preserving record linkage and privacy aspects of record linkage or data linkage. Any questions? We have almost half an hour before lunch, and I've only got a few more slides. So, yeah.
So I have a question. It's not really about this talk, but just about the record linkage literature,
Yeah.
which I'm not at all familiar with. So I was wondering if there's work in this literature on the dealing with the issue that the choice of a particular linkage technology might advantage or disadvantage certain, say, ethnic groups, because it might simply work better for some groups than others. Issues related to this. Have people worked on these kinds of
So the question, so it's really about, for certain types of data, what algorithms to use here. Very good question. I'm not aware of very specific studies which looked at for certain types of data, these techniques works better than this, right? I mean, there's been a few studies comparing linkage systems, but I think the problem with this really is that where do you get the data from, right? So let's say you have a French database, you have a German database, and an English database. Which linkage techniques works best? Which string comparison? The problem is you don't really get access to all these different databases. So how can you compare?
Do you know anything about different practices in different countries?
A little bit, and actually the questionnaire which we want to send out, so we actually have an idea of sending out a questionnaire to everybody here to actually collect what do people know about repositories, about data sets, about systems. We should send it out soon, I guess, yeah. So it's, again, not much is being published as far as I know in what actual systems people are using. Yeah, I don't know, Ron, you got no bit of
an answer to a question. I'm not sure if it's your question. There's a rich literature in epidemiology on what kind of groups are being missed by record linkage or which are producing false positive links. But that's all, and nothing of that literature is specific to privacy-preserving record linkage.
So I think that's a partial answer. So I think my question even sort of becomes relevant before you even think about privacy-preserving record linkage. Just this question of whether or not fixing a linkage technology is actually disadvantaging certain groups. Can you detect that? Can you compensate for that? Can you audit for that? Whose responsibility is this issue? Because if the decisions you're making eventually, as a result that come sort of many steps after this linkage, affect people's lives,
yes.
this matters.
Yeah, and I think, is Harvey here? No, Harvey's not here. So Harvey Goldsmith, he's talking tomorrow. He's done quite a bit of work in this. The uncertainty we get from the linkage step, how is this going to affect any follow-up studies? And unfortunately, the people who do the linkage are often a different group of people who do the analysis later on. Right? There's often a complete disconnect, and if you get linked data, you don't know how good the linkage quality is, how it was done, what are the biases and things like that. So that's something which there's definitely much more work needed, right? So
I'm going to talk about that partially in my talk, which is on Thursday, because we've worked on it with medical data, official statistics data, and also with data from the Syrian conflict. And it works on all three, and it works pretty well. So I'll talk about a lot of different things, but we have one new method, which we've partially archived. It's a Bayesian method, clustering method, very general, where it works on a lot of different types of data. So, but I can talk to you about it more.
okay. Any other questions before we wrap up? There's a few more slides here.
It's not connected to privacy at all.
That's okay.
Once you get a linked record, sometimes it's interesting to decide what's the action that you should attach to the record, for instance, the address.
Yeah.
So how do you decide which is the correct address,
Okay.
the most updated or
Yeah.
whatever?
Okay, good point. So that's basically a merging step, right? So once you've linked the record, you have different pieces of information. Again, it's very application dependent, right? So let's say you want to, in a business mailing list, with regard to addresses, that's why you want to take the most recent one, right? If you want to send out advertisement or letters or so. If you have several records, you want to might take, if you know something about the quality of the database, you might want to take the value from the higher quality database. If you have inconsistent values, it depends on the application, right? You might be able to use both, calculate averages, take the maximum, the minimum. It's very application dependent, right? There has been a bit of work in computer science to take that merging step into account and basically merge records and then use the merged records to link. So basically it's an iterative step. You link records, you merge them, use the merged records to add more linked records in and things like that. And actually one of my PhD students at the moment is looking at this from a temporal aspect. So if you have data which goes back in time, and again that's something which hasn't really been looked at, and you know that people move around quite a lot, right? So in Australia, something like 25% of people move every 5 years or something like that. If you know that, then it doesn't make sense to give a high similarity to addresses if an address is 3 years old, right? So we can modify the similarity calculations or the classification But then if you have data going back quite a long time, maybe simple example is a woman gets married, changes her name, a few years later on she divorces and goes back to her original maiden name. Then you have that sequence, and it maybe makes sense to kind of looking at all the past records of that person, and then look at what's the best match you're getting, right? So there's still open questions about how to best link such temporal things, how to merge things. It's again, there's a whole research area called data fusion, which looks at this as well, right? So how to best fuse the data together, to use what values to use of the linked records, and it's really application dependent, I'd say. Yeah.
The question that was asked about ethnic groups and nationalities made me think about whether there would. Here was the example I thought of. If you're somebody who is a foreigner in a country where the dominant language is English, for example, the chances are that your record your surname is probably going to be misspelled, or because it's not a common one, which would mean that if you were trying to link a person like that, you would a priori know that their distance might be bigger.
Yeah.
So could you build in a kind of metric that allows the distance to depend on the person's characteristics? Would that be a neat thing to do?
I guess you could. Again, it comes back to these learning techniques, like I mentioned before. You can learn the edit distance, the weights for certain edits, right? You could also do this at the level of, you can give, again, an extension of the Felici-Santro method is to give specific weights depending on the frequency of names, right? So you give different weights for Smith compared to the Dijkstra's, right? So you can extend this as well, right? If you have training data, you can learn a lot of these parameters, right? Again, it's a very data-dependent thing. Again, John, you must probably know more what you do at the Census Bureau, right?
What I was going to say is that there's a Becca will talk about some of this, I think, but there's a more formal mathematical way of thinking about this problem that I know that you use, but which generally summary talks about how to do record linkage, don't get back to. So, I mean, if you think about this using hierarchical Bayesian models, then at the end, the natural thing is any pairwise comparison has a posterior probability of being related to one of the virtual entities in your virtual population. And if you can formalize that and then manage to implement it, then you know how to do any analysis that's based on the linked data, and you know how to approach questions of bias and error in the inference. It seems to me that kind of formal way of thinking about the problem hasn't gotten nearly as much attention as it should have. I know that we are doing things at the Census Bureau, and I get questions from outside experts all the time about this, that imply that we're going to deliver to the research community a very high quality, exact linkage of the censuses that have been taken in the United States, back as far as we can go, with the unfortunate case of the 1890 census, which we won't talk about, excluded. And outside the firewall, research teams work on them from the published records. Inside the firewall, research teams work on them from what's in the archive. But they do not deliver to the research community any way of assessing the quality. And I routinely ask Bill Winkler what we ought to do about this, and he says it's still an unsolved problem. It's about 10% solved. So it seems to me that it's such a high priority problem that even if it's only 10% solved, we have an obligation, especially to future users of these research data products, to think harder about how we convey something. And to that end, I think some of the recent work on big data methods, combining design studies with found data, offer some guidance in how to do this. That they don't treat anything as an exact match, but they do treat everything as potentially informing that posterior predictive distribution that combines all the things. And when you are at a loss to understand how to compare some batch of found data to a population that you think you understand, that means you need to construct a small designed survey of that population that contains the variables that you can use to correct your found one. A lot of those methods, it seems to me, are applicable to record linking just as much as they are to combining data sources.
Yeah.
And I guess I'd like to encourage people to think more about that. I certainly know it's a very hard problem, and that I get a lot of questions about why we don't supply measures of error on our linked records.
Yeah.
And I think it's because it grew up from the unduplication problem in household
Yes.
censuses, and so there was a good reason to believe that the original census and the coverage survey were about the same population, and exact record linkage techniques were probably going to be reasonable for unduplicating and for estimating overcounts and undercounts.
Yeah.
But in many other circumstances,
It's
that's
not,
just
yeah.
not the relevant model, and it seems to me we need to especially think about that and think about the probability model
Yes.
that we're using
Yeah.
when we do these record
Yeah.
linkages.
I think Harvey Goldstein tomorrow is talking about this.
Sorry?
Harvey Goldstein, I think, is talking about this tomorrow. I think he's done.
And then we'll have
Okay, not that
all
problem.
people
Okay.
talking about it.
Yes.
It needs to be
Yeah.
talked about a lot.
Yeah. Yeah. Abadan, you had some. No.
The remark on using the language or the characteristic of the person to use a different distance function. We've tried that. We used the base classifier for classifying the original language from which the name is coming from and using a different distance function. But the game was so small we even published the paper.
So much for that.
Yeah. So I think it's one aspect of so many different in the whole process. There's so many aspects you can tweak around a bit, and it's very data dependent, right? So. Okay, so I've got four more slides with kind of some conclusions and research directions, and before we talk about some of them, and I guess maybe that's something we can talk later in the workshop and throughout the next few months. Having worked with historical census data and just historical data, I think data quality is a major challenge, and this whole thing of data cleaning. I know that historians spend a lot of time manually cleaning data, and that's where the computer science and the statistical community can contribute, coming up with semi-automatic, or I don't think it's ever going to be fully automatic techniques. I mentioned before the collective classification techniques, which have been used in bibliographic data, where you have authors and papers and the relationships between them. Not much work has been done on using these techniques on personal data. I've tried a bit of this on historical census data, and they don't really work because you don't have these relationships. So for me, it's an open question: can we actually how do we use relationship information between households, families, to improve, or to have collective techniques? I mentioned several times there's no training data available. I'm not sure if we can overcome this ever. I think employing active learning techniques is one way. I'll talk a bit about this tomorrow. I think visualization is another aspect where looking at these possible matches or potential matches, instead of just showing two records, it's about the environment. So like if you have household data, do the households look similar? Have people shared an address at some stage in the past? But how do we visualize this in a way that it helps people who do the clerical review to come up with better decisions? Linking data from many sources is, I think, very challenging, both from the actual computational aspect, from the statistical aspect, but also from the privacy aspect. Frameworks, it would be nice to have frameworks which we can plug in algorithms and then basically compare algorithms. So that exists in data mining and machine learning, but we don't really have that in data linkage. So I can implement my algorithm and then compare it on a set of test data sets. That would be really nice to have. Collections of test data sets, again, that's related to the framework aspect, I guess, right? So again, that's probably in that survey we're going to send out, asking what kind of data sets are people actually using. There are a few research groups which have data sets available. They're mostly in the bibliographic area or consumer products. It's of course very, very challenging to publish real personal data, right? Coming back to most of the question from before about the privacy preserving record linkage techniques, there's still many aspects of that which have to be solved before we make these techniques practical. The standard measure of privacy, right? We don't really have that. How do we measure, how do we compare different techniques? Most techniques in privacy-preserving record linkage use a simple threshold at the moment, so a dice coefficient for Bloom filters. If the threshold is above a certain value, then we say it's the same person, otherwise it's not. And I think the questions of how to assess accuracy and completeness in a privacy-preserving way is also an open question. So we don't have truth data, we only have hash-encoded values or Bloom filters. How do we know how good a privacy-preserving linkage is? We can't really assess this unless we go back to the original data, but we can't do that because of privacy and confidentiality. And then the last one, which I think we already experienced in today's discussions, is the collaboration across research disciplines, right? So where people with different backgrounds have different understanding, maybe talking about the same things. I certainly found this when I was started to work with social scientists. It can take several months to actually understand what do you actually want, and it's challenging and it's fun, but it's something which we're going to encounter in the next few weeks and months, right? Okay, and I'll just finish up with this slide here. Maybe not of interest to statisticians or computer scientists, but this is more about the application of data linkage in the whole aspect of reconstructing populations. So this came out of a workshop a few years back in Amsterdam. And again, it's a multidisciplinary book with people from the social sciences, linguists, who all specialized about how do we link historical data. And it's quite an interesting workshop and a quite interesting book. So I think that's it. So I'll end up here with a bit more time. I think the slides are going to be uploaded. They recorded my presentation. Don't listen to it. Yeah, thanks for great discussions, and I look forward to the next 6 months.
I have a question. What are your other 15 slides?
Yeah, okay, these are just
Show them to.
these are just the references. It's a collection of references, and more references, and more references, and more references, and then that's the end of it. So I didn't want to go through those.
So lunch is in Wolfson Court, but there are these two categories which I don't really understand.
Prepaid and not prepaid, right?
Something like that. Yeah.